All right, then let's get started. I hope you all enjoyed lunch. Let me probably go over here. And I was a little bit afraid because maybe it's kind of a niche thing here today at this conference, which is kind of special. Let me first ask some questions. How many of you are writing software which is deployed in production and actually used to make money in your company and businesses? Okay, quite a few. How many of you are maintaining such applications on a day-to-day basis? Okay, and how many are doing both? Okay, great. So, especially if you're doing both, I think this talk will have a lot of information for you. In contrast to lots of other presentations yesterday and today, this one is purely coming out of practical feedback and knowledge from people who are building resilient distributed systems. If you are using Erlang, for example, you will find a lot of mechanisms in this talk that you'll also have in Erlang. But all of the patterns I'm showing you today are completely applicable to any type of language. I intentionally tried to keep it abstract so you can take home as much as you can from this, and then you can apply it to your specific languages. So I work for Couchbase, and we make document-oriented databases. And I'm maintaining our JVM driver. And as part of that, I'm also working with a lot of our users and customers, trying to help them build resilient applications. And that was my main motivation, actually, because I saw so many user code out there which was so bad in terms of resiliency and reacting to failure that I figured let's do a talk there and step back a bit from the actual implementation, try to get specific architecture and patterns in place first that you can then apply to your applications. So let's get started. The most important thing, in my opinion, is that you need to get into the right mindset when you're building fault-tolerant applications. I don't care what language you're using, but you need to make sure that you are getting into the right mindset. You need to get into a fault-tolerant mindset, okay? So the US Marines, or actually military, there is a quite common saying. They say the more you sweat in peace, the less you bleed in war. And if we think about that in terms of software development, of course, thankfully, not many of us need to actually go to war, but you end up in the same situation. If you do not take care about resilience in your applications during development, it's going to hunt you in production, and you don't want to get the wake-up call at 3 a.m. in the morning that your production system is down. Or to put it in the words of DevOps Borat, 90% of DevOps a failed simple interview question of what is most critical piece of infrastructure is outgoing mail on Nagios server. So you definitely do not want to end up in such a situation that you're actually depending on your Nagios server sending you emails and that you implement fault tolerance that way. So joking aside, what I see out there most of the time is what I'd call sunny weather coding. People are developing the applications and they don't, because it's hard. It's hard to think about fault tolerance and resiliency because you need to not only apply a timeout here and there, you need to actually have a holistic approach if you want to take it really seriously. Now, what I also see is that a lot of people are saying, oh, I'm doing unit testing. I have 100% unit test coverage, so I'm safe. And I say, not so fast, Mr. Fancy Tests, because the problem is that, as you probably all know, that with unit tests, you can only prove that a specific bug is not there anymore, but there will always be bugs, which means there will always be faults in your system. So we need to accept the fact that there will always be faults. And in this talk, actually, I'm going to show you what you can do when a fault gets active and an error happens in your system, and then what you can do with those errors. So always ask yourself what can go wrong in any kind of situation. When you're building a new system, when you're building a new feature, really take the time and sit down and say, okay, this is the basic requirements. Okay, I got it all nailed, and I'm sending requests to this service, and I'm getting a response. What happens if no message comes back from the response? What happens if 2 messages come back? Or what happens if the response that you get from this service is actually not what you're expecting? Who of you has actually talked to a REST or HTTP web service and you expected JSON to come back, but what actually came back was HTML formatted response because you were hitting a server bug or something? Yeah, quite a few. And this is also one type of failure. Most of the time when I talk to people about failure, they basically think of failure as the system is down. But there are so many different variations of failure, and this is all covered basically under fault tolerance. So let's take a step back and try to get the wording in place first. So there are specific terms that when you talk about fault tolerance, which makes sense to get on the same page. So when we talk about a fault is a latent defect in a system, and when it's activated, it can cause an error. This is your typical bug. You have a bug in your system, you don't know that it's there, and then a specific condition, like a method call, triggers the bug, the latent defect gets activated and gets promoted into an error. Now, since we just agreed on that faults are always there, errors can always be in our system. So what we actually need to do to get resilience in our system is to handle errors. And what we need to accept is that those errors are the manifestations of faults. And when we fail to prevent errors from spreading and so forth, when we do not contain them and we do not mitigate them, then they basically get moved over and what we call a failure. And the failure is nothing more than a failure to comply with our specifications to our system. Now, a specification can be anything. You can say, when I do this request, I expect this response. That's basically a specification, but there are a lot of other subtle things, like what response times do I want from the system? I want 5 milliseconds on 99th percentile, for example. What happens if I have to wait 10 milliseconds and so forth? So, and this implies another thing. You actually need to think about your specification, because when you don't specify upfront what you're expecting, it's very hard to determine what failure conditions can be in your system. So, upfront, when you're designing a feature, make sure to also have specifications in place so you can actually measure the deviation from your specification, which is also quite important. So errors are inevitable, and what we need to do is, our main goal during this talk, and what you should also do is, you have those errors in your system, and make sure you detect them, recover from them, and potentially mitigate them before they become failures. Because when it's not a failure, an error is happening in your system, the system can still work, right? There can be different things like, for example, your system is not responding anymore 100% to 100% of the load, only to 90% and so forth. So, but as long as you can control your errors, you can put them basically in the spot, and you can recover from those errors before they become failures. You're safe, and this is the ultimate goal of fault tolerance and resiliency. Now, what is reliability? Because reliability and availability are very often confused terms. So when we talk about reliability, we mean the probability that a system is performing failure-free for a given amount of time. Okay, and there are two metrics to that, which is the mean time to failure and the mean time to repair. Now, for example, let's take a completely different example. Let's think about the Mars rover. Okay, the NASA probably wants the mean time to failure for this thing very, very high, because when they deploy the Mars rover, they want to do all the missions, and they don't want the Mars rover to fail before all the missions are completed. Probably they don't care so much about the mean time to repair, because it's quite expensive to send a crew over to the Mars to fix the Mars rover. Now, let's take another one, aviation and airplanes. So the mean time to failure should be, of course, longer than your flight duration, because you do not want to have the GPS system failing during your flight, right? But those are quite important metrics to figure out also in your software system. And if we think about airlines in the mean time to repair, they also want to reduce the mean time to repair so they can put the airplanes back into service very quickly, right? But if the GPS system fails on the ground, then the staff can fix it and so forth. So those are very important metrics to think about in your application scope, especially in terms of SLAs and so forth, that you meet those requirements. Because when we talk about availability, which is the percentage of time the system is able to perform its function. So this is most of the time, most of you will probably notice the number of nines that you commonly talk about when you talk about availability. And how can you calculate availability? Well, you take the mean time to failure and divide it by the mean time to failure plus the mean time to repair. Which means that if your system would take no time to repair, you would have 100% availability, but yeah, that's not going to work out. And typically in applications out there, the mean time to repair is quite high, because I mean, of course you can restart the service, but if you have another type of bug, then you need to fix the error and redeploy an application and so forth. So reducing the mean time to repair and actually increasing the mean time to failure is what we are looking for here. So talking about availability, this is what the common expressions are when you talk about availability. So for example, if we say we want to have 3 nines of uptime per year, that's basically 530 minutes of downtime per year, which seems quite okay. Now, 4 nines is like 1 hour of downtime per year, and most of the companies out there actually cheat when they have such tables, because they say, oh, we have 5 nines of uptime, but we do not count maintenance, right? Which, I mean, the system is down when you're maintaining it anyway, so you really need to count it into it. But if you are using, let's say, services online and you're really looking for availability, make sure they do not include or they do not explicitly exclude maintenance. And then we have 5 nines and 6 nines, and you can see in this area, this is already very, very tricky to get right, especially in distributed systems. 5 minutes of downtime per year is nothing, right? In that area, you will commonly find telco equipment, for example, with highly redundant components and so forth. They most of the time play in this area. And this is an important implication, as we'll see in a bit. So let's do a quick quiz. Let's say we have an edge service, and our edge service strictly depends on the user service session store and data warehouse. For example, a request comes in, and then we need to check, is the user actually registered with our system, and then we check, does he have a session active, and then we also grab some data out of our data warehouse. So what we want for edge service is 4 nines availability, which is around 1 hour of downtime. So what do you think each of those services needs to have in terms of number of nines to actually guarantee our availability over here? Any ideas? Who is for 4 nines? Exactly. And actually you, okay, I tried to. Okay, so it's not 4 nines because you are actually, you need to combine the availability of all of those. So it's somewhere between 4 and 5 nines. I didn't actually calculate the exact number. But the thing is, I mean, number of nines doesn't really sound like much, but if you compare 4 nines to 5 nines, or even to 4 nines and the 5, it's actually, you go from 1 hour of downtime to whatever, 10 minutes or something, or would be like 30 minutes or 25 minutes, something like that. And there is this buzzword microservices, right? Everyone is deploying microservices right now. And if you take this picture even further, here we're just talking about 3 services, but if you deploy microservices and suddenly you have 50 services in your application landscape, and they all depend on each other, and if one of them goes down, the whole thing actually can collapse, which is what happened to Netflix, for example. There are a lot of talks online from Ben Christensen, an edge engineer from Netflix, which is a really great guy, and he talks about, originally they had RPC architectures and not all the specific things in place that we're also talking about today, and if one of the services failed, it was like, because they had thousands of requests per second, they couldn't even react, the whole thing was actually swamped, and they couldn't do anything anymore, right? Because even, let's say you're using thread pools with hundreds of threads. If you have thousands of requests per second, and each of those calls blocks on a service that is not available anymore, your thread pool is also blocked, and then your dependent service is also down. So if you do not take care, you can very quickly spread issues across your system. So, any questions so far? All right, let's keep moving. So, now we agreed that we need to think about fault tolerance and so forth. So let's now talk about how can I architect my application to be fault tolerant. So the first thing, and now I'm going to talk about patterns. So the first pattern, which is, I would say, required for all of the thing that's coming now, is the unit of mitigation. And the unit of mitigation, the idea is that you have a specific unit which you can use as a basic container for error containment and recovery. So I can't tell you for your application what this unit of mitigation looks like, but the only guidance I can give you is that it should be large enough that you can potentially fix errors that are coming up in this unit on your own. It shouldn't be so small that you cannot do even error handling, but also, of course, it shouldn't be a whole application. So especially if you're doing domain-driven design and so forth, picking domain objects and actually grouping them together is a nice rule of thumb. So pick a unit of mitigation that you can And we'll see in a minute how those patterns look like, so you get a better feeling of how large the unit of mitigation should be for your application. But if you do not have those defined in your application, it's very, very hard to do things like redundancy, for example, because what components do you pick to be redundant? You don't know, right? If you do not pick units of mitigation, or if you have failover in your application, what parts of my system do a failover? So this is the basis for all of your application. And there's another term, I think they had it in the old Reactive manifesto, which was called bulk heading. So they had this picture where you have a ship, and the ship has compartments. So if some of the compartments fill up, the compartments actually prevent it from filling up the whole ship, right? So you want to make sure that your units of mitigation can potentially recover on its own and do not take the whole thing down. Now, when you are not able to recover inside the unit of mitigation, what you want is you want to have a clear escalation path. So if your recovery is not possible, inside unit, you need to escalate it to someone else, because you don't want to fail the whole thing. Very often, the parent scope has more information and can do much more intelligent failure handling than your single unit, because the more information you have available, the higher the chance that you can actually recover from an error. Now, to give you a concrete example, this is from our Java SDK. And if you're, so a quick 1 minute intro into Couchbase. So you have a cluster, and you have a cluster of nodes, and each node in the cluster has specific services, like key value query, and you can do secondary indexing and whatnot. Now, when we architect the SDK, we thought, let's use the same terminology, and then you can apply those units of mitigation and escalation paths very easily. So our endpoint here is like a socket. Okay, so it's a wrap around the socket, and we can do basic error handling here. We can say, if the socket is down, then we probably retry with an incremental backoff or so forth. And we can do that. And maybe it turns out, hey, it doesn't work, right? The error comes up over and over again. What we can then do is we can escalate it to the service level, because the service level probably has more than one endpoint here. So it can infer, for example, this service maintains 3 endpoints, so 3 sockets, and only one of the sockets is down. It can probably infer, the remote service is still back up, so I keep retrying this one. But if the service sees that all of the endpoints at the same time disconnected, there is probably something wrong with the node on the other side of the network. So it doesn't make sense to keep retrying immediately. Maybe it schedules a retry with a longer backoff, or it even notifies a different component which checks a new configuration from the server to see if the node is actually part of the cluster anymore, because it has been failed over or something like that. Now, if this, and then it goes on and on. If the service has no clue what to do, it propagates it to the node layer, because the node knows about all of the services in the cluster. And this architect, very simple example we had. So a service, of course, talks to a specific port on the node. For example, there is 8091 for HTTP communication and 11210 for key value binary operations. Now, what can happen is that not every user uses all types of operations at the same time against the cluster. So someone is only using key value type operations, someone is only using views. Now, what we had in common setups is that they had firewalls in between, and the firewalls silently shut down connections that were not active. So if you're only using key value traffic and not indexing traffic, this service would be completely would be closed, because the firewall closed all the connections after, let's say, a few minutes. So you know that, you don't know that at the service level, but you probably can infer that at the node level, and then you have more scope, and you can you have more information available to guide your error recovery mechanisms. And then finally, if we have an error at a complete node, we propagate it to the cluster level, so the cluster knows all the nodes and can then determine what to do. Most of the time at the cluster level, when a node goes completely down, we grab a new configuration from the server and see if it's actually still part of the cluster anymore, because someone could have removed it, or it could be forcefully removed because the node has been failed over or something like that. So let's talk about redundancy. Most people think about redundancy only in terms of hardware redundancy. But you can build redundant components in software as well, of course. So, and there is, your trade-offs here are cost and time to recover. So if you do, and this is true for both software and hardware redundancy. If you do active redundancy, of course the cost is high, because you need to have all your redundant services running at the same time so they can immediately take over. But the time to recover is very low, because they can immediately take over. Another approach would be active standby. So the cost is still high because you need to keep your nodes running, but probably they have a warm-up time. So if you use active standby components, your standby component probably is powered up, but it doesn't get all the traffic all the time. So it needs some time to maybe warm up some state or so forth to actually be able to serve traffic. Now, and then there is n plus 1 or n plus m, how do you want to call it, active passive redundancy, which means you have standby components, and if your active component goes down, then you power up the other component, and then it takes over. Of course, this takes the longest time, but it also reduces cost because you do not need to run all the services at the same time. So depending on your requirements, you need to pick the right way of redundancy. Now, one thing that is very important is, and I think this is a concept that not many people proactively do in the applications, is what it's called a fault observer. So what you want is you want to have a centralized observer which receives system and error events, and in turn, it can guide and orchestrate detection and recovery. Because imagine you have lots and lots of those units of mitigation in your system, and they all get errors. Now, they could be in different places, and they only have their own scope. So if they all send the errors to an observer, the observer has the knowledge of all the errors going on in your system, and then can do a much more informed way to guide your error detection and recovery, right? And another very great thing about this observer is that you can actually add listeners to your system. So if I have this observer and I'm already taking the data, I can very well let users of my system subscribe to the service so they get notified of errors in the system. For example, they can listen to this observer and then push it into Graphite or Nagios or their monitoring system to do proper monitoring, right? And because otherwise they would never have this information available. Most systems out there, they just log. But logging doesn't allow you to do proactive error recovery because someone needs to parse the logs and then do something. It's too late at that point. You really want immediate feedback to guide error recovery because you don't want to have the worst thing you can do is have users as part of the error recovery process, right? Never do that. What you want is you want to minimize human interaction while you're doing error recovery, but you want to maximize human participation because at some point someone needs to fix the error that happened, right? And this user needs lots of information available to make an educated guess what actually happened, right? So error recovery, quick and fast, make sure the system keeps online and doesn't fail. But then at some point you also need to make this information, this probably a boatload of data available to users to fix it at some point. So one application, one example from our SDK, the specifics are not so important. So you connect to the cluster, and this is just regular Java code, and then we expose an event bus. And in this event bus, so for example, we log connected to node A, for example, but we also push this information to the event bus. If no one subscribes, well, no one cares. But you can subscribe to this event bus and get those information immediately, and you can push it to your monitoring system, for example, if a node goes down and so forth, and then you can do something with it. Because all of this information might be very valuable to your system. Because if you see nodes are coming down, and then we had this escalation path, because your monitoring system of your whole network and application landscape has more knowledge than each individual application container. And then you have a system administrator sitting there saying, oh, actually, this core switch went down. This is the reason why this and this is happening. And then he can make a much more better educated guess how to quickly recover from the error, right? So it's all about escalation and aggregating more knowledge as you push it up to the next boundary. So that's the basic points of architecture, and there is, of course, lots more to talk about that, but we only have 45 minutes today. So what we now want, we want to detect errors as quickly as possible, and I really like this thing. A silent system is a dead system. Even if your system is working perfectly, but no one actually knows that it's working perfectly, you could assume that it's dead. So make sure that when you are building an application, it pushes information to a monitoring system. It's pushing metrics somewhere, so that you can actually get insight and confidence that your system is working properly, which also has a feedback loop. So if you're pushing out a new feature or making performance enhancements, you want to have a dashboard with metrics to see if that fix actually made it worse or better and so forth. So even when it's humming along nicely and there is no failure going on, make sure to push data somewhere that you can actually do something with it. Now, what you want to have is some form of a system monitor, right? Which takes all this data and presents it to you in a nice fashion. It shouldn't be as elaborate as mission control in Houston, which is actually a very nice place. And this system monitor really helps you to study behavior and make sure it's operating as specified. So not if something goes wrong, but also during regular operations. One example here is a project from Netflix called Turbine and Hystrix, which if we have time, I can show you in real life as well. And what they do is basically they have this dashboard. And you can see there are circuit breakers. We'll talk about circuit breakers in a bit. And they provide you per second real-time feedback of your whole fleet of servers. So they have thousands of machines running, and they want to get immediate feedback. So this turbine is actually aggregating all of those circuit breaker information, and they can see at second precision for every, let's say, type of operation they're doing. For example, here they are fetching some titles, and here they check some social status and iTunes client login with receipt and token and so forth. And you can immediately see how much traffic is going through. Are there any errors? You see the percentile. So actually looking at this dashboard gives you a lot of information. And what you can also see very quickly is that if something goes wrong, this thing goes from green to red. So if you have a system administrator sitting there and it sees basically this one is red and this one is red and this one is red, it can probably, because it knows the context of your application, oh, those three are down, then it's likely that this and this and this happened, right? So the more information you make available to users, the much better, because then you guide error recovery. Now, one other very important thing is periodic checking. So there are two things which I'd like to cover. The first one is heartbeats. So you can use heartbeats to monitor tasks or remote services and initiate recovery. So you probably all know heartbeats, right? You have a system, you send a heartbeat, and if no heartbeat comes back, then probably something is wrong. Now, in practice, it's a little more complicated than that, because it could happen that the response comes back after a later amount of time because the other system is just overwhelmed of work. So you need to find the right scaling for your things, because let's say you miss one heartbeat, you do not want to immediately trigger error recovery and whatnot. Maybe you want to wait a few heartbeats to actually make sure, or to increase the percentage that the monitored system is actually down. Now, another thing are routine exercises, and this is less common than heartbeats, but I think it's very important. You need, when you have components in your system, maybe standby components or just components that are not utilized on a regular basis, you need to make sure to give them some work to do to prevent unit starvation and also to surface malfunctions. So, for example, the example I brought to you earlier with the firewall, that's exactly the same thing. We can prevent that, because if the user is not doing key value operations, we can every few seconds we can just send an operation like a ping to the server. So hey, everything is fine, and this will prevent the firewalls from closing the connection. So by applying those patterns consistently, you can actually mitigate a lot of those side effects that you'd get up front. And what you can also do with those routine exercises and heartbeats is not only checking that a response comes back, but you can actually piggyback on top of that, and you can say, I'm actually measuring the latency. And then you can take this average latency that you get for your pings, and then store this metric somewhere. And then, for example, if you suddenly see that the response time for the heartbeat, is longer and longer, you can actually alert that as well. Because then there's probably something going on in the network, or some of the servers are overloaded, and then you can add new nodes to the cluster and whatnot to actually mitigate the situation. So, and this is what we are doing in the Java SDK. So, has anyone heard of Nettie, the Nettie IO library? Oh, quite a few. That's great. So, we are using that under the covers, and it has something very nice, which is called the pipeline. So, when you're doing network traffic, you do not want to care about all the event loops that's going on. You actually want to transform your data from raw bytes into an N format. So this is what you do. You basically define encoders. So we take a request, and then we encode it into some byte format, and then we send it to Nettie, and then it writes it. And when the response comes back, we pass it through a decoded chain. Now, what we can do here is we can actually put in here a handler. In Nettie, it's called idle timeout handler, or something like that. So after a specific amount of time, if no traffic went through, it's sending a message up here saying, hey, there's no traffic going on. And then you can proactively send another request. And this is what we're using, actually, to do those pings on a regular interval with not very much things you actually need to do. That's kind of nice. So if you are working on the JVM and you need an I/O library, use Nettie. Shameless plug, but it's actually I evaluated all of the I/O frameworks on the JVM. Nettie is hands down the best one. So yeah, I can just recommend you that. Oops, that was not the one. Huh. Yes.
So Nettie is also providing some kind of scheduling, like capability that is it's idle for a long time.
Yes. So actually, in Nettie, I'm probably going a little bit off topic just to cover it quickly. So in Nettie, what you have is you have event loops, and what you actually do is you schedule tasks on the event loops. Such a task could be write this request down to the socket, or it could also be like you have a scheduled event executor. So a scheduled executor in Java, which you send in a task and say execute this after a specific amount of time. So what it actually does is every time you write something, it resets this content. When it fires, then you know nothing happened in that period, and then it sends up a message. So it's quite easy and reasonable to use. If you are putting in that handler, what it does is you just get they call it a user-defined message. So and then you can react to it. So the next thing is writing over transients. So very often when you're dealing with recovery and you're implementing those mechanisms, you should not fall into the trap to, for every single blip that is occurring in a system, react immediately. There's a very fine line between waiting and also waiting too long and not waiting too long. So what you want, so Robert Hanmer, which wrote a very great book, which I'll have referenced later on those patterns, he says, patience is a virtue to allow the true signature of an error to show itself. So sometimes when you wait a little longer and it's still in your SLA period, probably you can infer a specific, how do I put it? If you wait a little longer and you accumulate those errors that come up, you can identify specific patterns that you probably couldn't if only one error of them came out, right? So this is very, I would say, specific to the error handling in the application. But just keep in mind that sometimes you want to wait a little longer, especially if you can afford, then you have more scope or more context available to guide your error recovery than just doing it immediately. And one way to do it is the leaky bucket. The leaky bucket is a pattern which you can implement. And you can think of it that way. So you have a bucket. And let's take requests and responses as a simple example. So when you do a request, you put data into the bucket. And when a response comes back, you basically have a hole in the bucket and water drains out of it. So if our bucket is designed to make 100 requests per second, we would have 100 requests go in and 100 requests go out, and our bucket is fine. Now, imagine we are doing more traffic, but we cannot really handle it. Our bucket would overflow. And then the drain rate is too slow for a thing, and then everything would just overflow. So you can use the same pattern for error recovery. You can say, I allow 5 errors per second on this specific application or this specific unit of mitigation or this specific task that I'm doing. So you are counting those errors in the bucket, and then you have a drain rate of, say, two events per minute. Because what you do not want to do is, you have a counter in the application which counts the errors. And your logic says, if more than 5 errors happen, trigger error recovery. But what happens if one error comes after 1 hour, after 3 hours, another error comes, and suddenly after 1 day, you had 5 errors in hours distance, and suddenly you trigger error recovery. You don't want to do that, because at some point you want to reset those counters, because there is a high chance that the system already stabilized. So you want to define a drain rate, which is like the normal rate of your system. And then so you can, it's also called a sliding window. So you can implement sliding windows in those specific errors, error handling time frames. So, and there is much more. So I can't go into detail of all of those, but there is, for error detection, you want to do very rigid parameter checking. So you make sure everything that comes into your scope is properly checked, and you make sure that everything is fine before you move on. You can use watchdogs. Watchdogs are like heartbeats, but they basically sit in between, and they watch the traffic going through. And if something goes wrong, they yell and tell you, oh, something is going on there, and then you can react to it. You can apply voting. So, for example, if you need to make sure that your result is correct, and you probably fetch data from from more than one source. You can, let's say you get back 3 responses. Then you can apply voting mechanisms, and you can pick the majority configuration. I can give you a quick example of that. So when someone connects to a Couchbase cluster, of course it needs to give us an IP address so we can establish an initial connection to the cluster. Now what happens if he gives us 3 addresses? And one of those addresses actually points to another cluster just because he messed up the IP addresses. Now, if we would just pick the first one, we would never know that we actually connected to a completely different cluster. Now, if he gives us 3 or 4 of those IP addresses, we can grab configurations from all of those nodes and then apply majority voting to make sure we actually connect to the cluster where most of the configurations agree on. It's not 100% foolproof, but it's something that allows us to be more intelligent and help the user probably to figure out the user error that he made at configuration time. Checksums are very commonly known, and also routine audits. So you, depending on the type of application you're doing, you sometimes want to have routine jobs which peek into, for example, data structures, especially in systems like C environments where you can have dangling pointers. You want to have some audits that actually looks into, let's say, a linked list and make sure that all the links are still in place and so forth, depending on your type of application. But this is more, this is very specific to your language environment most of the time. Okay, we detected errors. Some other questions on error detection? Okay, I'll just move on. This one is obvious, right? Okay, timeouts. Let's get through it. So you don't want to wait forever and clog the resource. So it turns out does everyone agree that timeouts are a good thing to have? Okay, yeah, hopefully. Now the thing is, and I really say this by heart, do this on everything. Add timeouts to boundaries of your system. Not only add it to a specific network call, but also add it to, let's say you're using a database library. You want to have a timeout there. Because I can tell you that database drivers have bugs. Your JVM or your runtime environment has bugs. If you ever check the OpenJDK Jira issue repository, I don't know how many thousands of bugs are open there. So do not trust your libraries. Do not trust your operating system. Of course, it's more likely to have a bug in your application, but there is a very good chance that something else is also messing up your system. And having timeouts is really your last resort, right? When a timeout happens, there is already something going on that you don't want to happen, unless you set the threshold very low. But always, in your system boundaries, use timeouts all the time. They are really your last resort of defense. They are, and here's the great reference back to The Walking Dead. So who has seen The Walking Dead? Only a few. It's about zombies, right? Do you have Netflix in Poland? No, okay. Oh yeah, okay. So it basically it's a series about zombies, and when they bite you, you also turn into a zombie and so forth. And this is really my only analogy that I could come up with, because I thought, oh, let's put zombie pictures in there, but finding zombie pictures which are not looking too nice and also educating at the same time is a hard task. So I just thought omit all of them. But again, really, your timeout is your last line of defense, that when your dependent system or resource is not available or it doesn't respond, you can make 100% sure that you can still keep going, right? Even if of course, you didn't get the response you wanted to, but you can at least take another request that came in and try again, or try a fallback mechanism and so forth. If you don't have timeouts, you just keep waiting and waiting and waiting. Your thread pools get also filled up, and then you go down the same way. Yes?
In one of the papers, in one of his presentations, states that the people shouldn't be in charge of setting the timeouts, so that it should be done automatically. It shouldn't be choosing the time, the period of time shouldn't be chosen by hand.
Oh, I think it needs to be chosen by hand most of the time. But you as the application developer, you need to, because what you normally, you know your average response times, right? And then you add a little bit of get to account for network latency blips and so forth, and this is your timeout. And what you can also do is you can set very slow timeouts, but then implement more retry functionality, basically. So you're expecting timeouts on a larger scale, but then on the other hand, you have better retry mechanisms in place to trigger those. So, or are you not agreeing with that, or?
Yeah, because we had a similar program that it wasn't obvious how to set the timeout, so it wasn't the timeout of the system on the response wasn't like very didn't have like fine average. It was sometimes it was a very short one and we needed to respond quickly, and other times we got the response. But
I see.
yeah,
So
we implemented the retry mechanism that with every with each retry we wait a little bit longer. So
yeah, no, that totally makes sense. I mean, if you have varying response times, I think if you're in doubt, use a higher timeout, but use one. Even if it's very high, let's say a few minutes, but then you can be sure at some point you back out, right? Of course, in your case, you probably then want to have more elaborate mechanisms like shorter timeouts and then better retry functionality. So you know, on average, I get this response time. Sometimes I have these outliers. I just stop and then retry again, right? So that makes sense. But in general, having a high timeout is always better than having no timeout at all, right? It's really your last line of defense. Does that answer the question?
actually, I just wanted to know your opinion on that because actually it seems that when thought it was looking something different. I don't know.
You can, I mean, if you want to get really fancy, you can also set automatic timeouts based on your traffic. For example, if you have this, if you know that on average your response times are 500 milliseconds, then you add some time. So you're measuring that basically like a heartbeat. You're measuring your latency of the heartbeat, and based on that, you set a timeout with of course, some more gap that you are accounting for. You can also do that, but most of the time it's fine if you set a static timeout because very often you know your average response times, you know your network latency, and then you can figure it out. Because it's really, at this point in time, something already is not as working as expected. So it's not so much more about giving the user perfect experience. It's really about getting back into a non-error state. So we had the redundancy stuff here, and if we're talking about redundancy, we also need to talk about failover. So what you want with failover is you want to basically to failover to the redundant component. And in hardware, so if you use servers with multiple power units and so forth, this is done for you. In software, you can do the same. In software, what's going to happen most of the time is that you'd have time-bound redundancy because most of the time you make a request, it doesn't work, you failover to another component, and then you make a request to failover service or something like that. So you can do that, but of course what you can also do is like active-active, but that's getting probably really expensive depending on the use case because you would need to make requests to multiple services all the time. If you do that because it's so precious, then you can use approaches like voting to actually get more out of your redundant requests. Retrying, that's another favorite topic of mine. So while true and retrying, or the functional equivalent, whatever, is not a good idea because without waiting, you're quickly overwhelming the target system. And since the target system is already in a bad shape, you're just overwhelming the system. So what you want to do is you want to wait until you retry. And there are three common ways to retry. The first one is with a fixed delay, like 2 seconds, and then you wait 2 seconds and 2 seconds and 2 seconds. But I'm not a fan of that approach, but it's the easiest one. And then we can do a linear timeout, but we can also do exponential timeouts. Actually, I'm a really big fan of exponential timeouts, especially when you do socket retries, because the first few times you want to retry very quickly, because it could be there's something going on the network, which is already gone away, and then you can retry to the service which is already up. But then if you see after a few attempts it's not coming back, then you really want to very quickly wait longer and longer, because it could be that your server is restarting and whatnot. And don't forget, with all of those, other than the fixed one, apply a ceiling. You always want to have a ceiling for retry timeouts, because otherwise, especially when you use the exponential one, after a few ones, you're already waiting 5 and 10 minutes and whatnot. And then the service comes back online, and you're thinking, my application doesn't work. Well, this thread is still sleeping because it's waiting for the retry loop. Okay? So always have realistic thresholds and boundaries. And then this is your last resort, right? You can always restart the system, but the trade-off for restarting is really you're losing state and you're losing time. I mean, the time one is obvious, but also state is quite important, especially if you have a system like a cache, and you're restarting the system, you're coming on with a cold cache, and then you need to spend the time actually warming up the cache before you can use the system. So this is why it's so important to actually make error recovery and error mitigation running in an online system. And of course, you're reducing your availability and reliability with restarting it. One other option, and this then comes back with failover, is that of course if you have parallel services and you have intelligent feedback mechanisms and your load balancer, for example, you can, when you know you need to restart the system, you can instruct your load balancer to redirect to other application servers. Then you restart that, you wait until it warms up, and then you put it back into your cluster. So of course there are ways to reduce the time, but restarting is always your worst case scenario. Another important thing, and now we are coming into mitigation in the first place, is you want to fail fast. You want to shed load and give, let's again take requests and responses because it's the easiest to reason about. You want to give partial of users a great experience instead all of them a bad one. So the classic example of this is unbounded queues, right? You have an unbounded queue, data comes in and you keep working it through. Now the queue gets longer and longer and longer, and everyone who is waiting there will never actually make it through because let's say they're running a timeout. Now what you actually want is you want to shed load. You want to say on your boundary, I have a fixed size queue, or I have a ring buffer with a fixed size, and whatever fits in that fixed size is fine, I'll take it, and whatever comes afterwards get rejected. Now, if you do that, if you reject it immediately, it's a good thing, because then your caller gets a chance to decide what he wants to do. Does he also want to back pressure the error to someone else, or does he want to implement retry logic? But if you let him come in your queue, and then you reject him 10 seconds later, this is 10 seconds lost where your caller could actually do something else in the meantime. Yes?
Doesn't go against the retries and the exponential...
No, because the retry part is on your caller side. But this part is on the receiving side, right? And if you do that, it's working perfect together. Because if you have fast timeouts and you have fail fast on the other side, you have very quick information exchange, and you can make very educated guesses on your caller side to retry or to back off.
Well, the question is, we are chaining the services, right? So the service itself is calling another service.
I mean, that's one way. But also, let's take the Java SDK, for example, also again. You are using a method call. You're saying, give me this document and whatnot. And inside, of course, we need to do a lot of matching. So what we have on the outer boundary is a ring buffer. Now, when we are overwhelmed, taking data out of the ring buffer and sending to the servers and getting the responses, it fills up and up and up because maybe you're just pushing too hard. At one point, when the ring buffer is full, it's basically like a future. And we will immediately cancel your future saying, oop, back pressure exception, something is going on here. And then it's up to you to decide, but we're still in the same JVM, right? It's not talking to another service. You can use the same approach. And this is where things like message passing come in so nice. Because when you're doing message passing exclusively in your application, you can apply the same mechanisms to a service that is running on another machine. Maybe it's running in the same JVM. You don't care. You can apply the same mechanisms. And you're much more pushed towards writing resilient applications. And this is why languages like Erlang are so nice, because they are kicking you directly in the direction to do this. For things like Java and so forth, you need to do much more manual stuff to get it there. But of course, you can do it in any language. So this is how we're doing back pressure. It's also quite important. Another effect, and I quickly want to cover this, if you're using bounded queues or ring buffers, you can use it to reduce the contention, and this is on your I/O devices. So imagine you have, let's say, producer threads. So your application threads are asking for data. They're sending requests into our Java client, for example. Now, if they all talk to the same I/O device or event loops, we would get a lot of contention on those. But what we can do is we're putting this ring buffer in the middle. And not only we can do very quick back pressure, but what we can also do is we have this one batching thread, which is taking data out of the ring buffer and sending to the I/O. Now, what it can do is when the subscriber is slower than the publishers, the ring buffer gets full and full, and when the subscriber comes back, it can take more and more data at the same time, put more and more data at the same time down to the I/O device, and in turn, we get nice effects like TCP batching characteristics and so forth. So these are ways to basically, by picking the right data structures, you can mitigate lots of errors in the first place. And you can make sure you're building intelligent applications that even they cannot really remove errors completely, but they can help you to get also out of an error condition much more quickly, right? And you're preventing things like contention and starvation in the first place by doing it like this. A quick thing like a case study, Hystrix. Hystrix is a library developed by Netflix to actually build resilient distributed systems. Now what they do is they have something called a command and it wraps your data. Now what it has a circuit breaker. And the circuit breaker works like this. When data goes through and everything is fine, the circuit is closed and it's just humming along nicely. Now there is a feedback loop into the circuit breaker which tracks latency, response times, and so forth. So it actually has metrics to work with. Now, let's say the request failed for some reason. The circuit breaker will open. So the circuit will open. And all traffic that's going through will be rejected immediately. There we are again with failing fast. Because if we get a bad response, and you can, of course, you can tweak those thresholds, saying after a specific amount of requests failed, I want to open it, and so forth. Now, if it's rejected, we fail our command immediately, and then it's up to the user what to do. He can define fallbacks. You can probably do another command and so forth. And then after some time, the circuit breaker lets one operation go through and sees, does it come back? If not, we keep failing. And then we basically, if this one operation succeeds, then we can put more and more on it, and then the circuit breaker will work again. So it's really a very intelligent way to fail fast when you have an error, and you get the metrics feedback loop at the same time. And if you, for example, use Hystrix, then you automatically have the dashboard that you've seen before because it's exposing these metrics, and then you can aggregate them. So you basically, you solve more problems at the same time. You have the fail fast and error handling characteristics. You have the fallback mechanisms built in. So you can do fixed fallbacks. You can fall back to a blocking call. You can fall back to an asynchronous call. So you can compose them, and then you also get the metrics. Now there is much more we can also talk about. There is recovery. So when you're doing error recovery, you can roll back, roll forward, checkpoints. You can do checkpoints in your code to make sure you don't have to roll back to all of the points. You can reset your data. For data mitigation, I already talked about bounded queuing. So you want to bound your queues. You can do expansive controls, so you can dynamically scale your systems if you need more resources, and you can shrink them down to make sure not everything starves. You can mark data as corrupted. Sometimes it makes sense to not trigger error recovery immediately, but also to mark a request as invalid. Just mark it and then move it over, because the upper service is probably intelligent enough to work with it, right? And you can use error correcting codes, which is more a lower level kind of thing. So, recommended reading. I have 2 books which I recommend for you. The first one is Patterns for Fault-Tolerant Software by Robert Helmer. If you like those patterns and the kind of things to work with, this book is really the way to go. It's not super dry, but of course it's more pattern focused. And then there is a book called Release It by Michael Nygaard, which talks about the same things, but in a more conversational style. He includes war stories from him working with airlines and so forth, what happened, failure and so forth. So this is, I think, if you want to get a nice start with it and then move over to patterns. If you're already into the topic, you probably want to check out the other book first. The other one is really more a reference also to go look, because you read it once and then you say, oh, there is this pattern. I look it up and then I implemented it. Any questions? Yes?
One, I know it's a general question and the answer depends, but usually what is percent cost when making application to make it resilient? Some reasonably complex application, non-resilient version versus the resilient.
So yeah, the question was talking about cost between resilient and non-resilient systems. So I didn't include this topic because it's a whole topic on itself. But of course, the cost is, for doing resilient systems, the cost is development cost, right? But you very strictly need to compare it to what actually does it cost my business when the thing is down, right? And if you make those calculations, very often the argument is towards building resilient systems, right? Because there is not only cost at the stake, but there's also reputation and so forth. Now, one thing I would suggest is also you don't have to, when you do this fault-tolerant checks and what can go wrong, you don't have to fix all of those, right? You can do 80-20 rule. Most of the time I can fix 80% of my failures, my errors, before they become failures at a reasonable amount of cost. And then the other 20%, if I know them, then I can quantify them and say, if maybe this event is not going to happen once in 5 months. Not worth fixing it. Someone will restart the server. Because fixing it will take like 7 weeks of work and no one is going to do that, right? So it's hard to quantify, but of course the main cost is during development. You need to spend effort architecting it in a resilient way. You need to implement those patterns. If you're picking a language which has some of those, you can reduce the cost, but of course it's there. My experience is that if you start early with these things and you already bake it into your architecture from a greenfield approach, the cost is much lower than if you actually bake in these things in a full-blown application which is already out there. If you do that, I would recommend starting with things like make sure on your boundaries you have timeouts, and then you define your units of mitigation, and then you see, oh, those parts in my system are the most important ones. Then you start with those, and everything you can apply from those patterns to make it more resilient is a good thing, right?
I think we need to finish on that because we are running out of time. There will be another.
Okay, then just talk to me afterwards.